After years of anticipation and numerous disappointments, the astronomical community has finally received confirmation. Barnard star, one of the Sun's closest neighbors in the vast cosmic expanse, has yielded its first reliably confirmed planet. This momentous event follows decades of intense searching, marred by countless failures and false alarms. Now, with planetology reaching an unprecedented level of development, the long-standing debates about the existence of planets orbiting this star seem to have come to an end. Thus, Barnard's star has solidified its status as the closest single star to us, harboring a rocky world potentially similar to our own Earth. This narrative will delve into the details of this astonishing discovery. Indeed, this red dwarf, located just 6 light-years away, is the solar system's second closest neighbor after the multi-star Alpha Centauri system. Despite its proximity, Barnard's star differs significantly from our Sun. Its mass is only 1/5 that of the Sun, and its surface temperature is 2,500 degrees Celsius colder. However, it holds the unique record as the fastest-moving star in the night sky. In just 90 years, it can shift its position by approximately half the apparent diameter of the Moon, a characteristic that has consistently drawn the close attention of astronomers for decades. Unsurprisingly, multiple claims of planet discoveries around it have been made over the years, yet none of these had previously received definitive confirmation. For instance, in the 1960s, a prominent, though later refuted, report emerged about a planet that turned out to be merely an optical artifact caused by the imperfections of telescopes at the time. In 2018, an international team of astronomers seemingly presented compelling evidence for a planet with a 233-day orbital period. But this, too, proved to be another phantom, as other researchers convincingly refuted the signal in 2021, explaining it as a result of natural stellar activity arising from the star's rotation. However, this time, the planet officially announced in early October 2024 in the authoritative journal Astronomy and Astrophysics is based on much stronger evidence, precluding the possibility of its erroneous identification with data artifacts. The authors of the current study dedicated years to targeted observations of this star, utilizing one of the most advanced and sensitive instruments specifically designed for hunting Earth-like exoplanets. They performed truly brilliant work in thoroughly verifying and analyzing the data, skillfully avoiding all the pitfalls and errors that befell their predecessors. As a result, we can now confidently speak of the existence of another rocky planet in our immediate vicinity. Meet Barnard B, a world whose mass is approximately 40% that of Earth, orbiting its star on a very short path, lasting just over 3 Earth days. This means its orbit is 20 times closer to its parent star than Mercury's orbit around the Sun. And unfortunately, these are not the most encouraging tidings for life as we know it. Even orbiting a relatively cool dwarf star, this planet should still be too hot for liquid water to exist on its surface. Scientists estimate that the temperature on Barnard B could reach 125 degrees Celsius (257 degrees Fahrenheit). Yet, the significance of this discovery cannot be overstated. Even if its orbit is closer to the habitable zone than ideal for habitability, it is still a rocky planet, and it is literally in our stellar backyard. Moreover, the cutting-edge technology astronomers used to achieve the necessary level of sensitivity didn't just give us Barnard B, it also hints that this world may not be alone in its system. Contrary to popular belief, not only space observatories like the legendary Kepler, TESS, Cheops, and other past and present telescopes launched by humanity into space are the best tools for exoplanet research. On Earth, there are also numerous powerful telescopes equipped with ultra-stable spectrographs that possess the unique ability to detect Earth-mass planets. The question of whether they surpass or fall short of space observatories certainly remains a subject of debate. The obvious advantage of space telescopes lies in the absence of an atmosphere, which distorts incoming light. However, adaptive optics on advanced ground-based observatories have reached such a level of precision that they can now effectively compete with space-based instruments, for which, incidentally, there's an enormous waiting list of tens of thousands of astronomers worldwide. Meanwhile, by working at a ground-based observatory, researchers can install scientific equipment of any bulky design without worrying about the mass and size constraints imposed by space launches. Such a unique piece of equipment is the instrument known as the Echelle spectrograph for rocky exoplanet and stable spectroscopic observations, or ESPRESSO for short. This is an extremely complex and incredibly precise device, whose main goal is to measure stellar spectrum oscillations with a level of accuracy currently unmatched by any other spectrograph in the world. At the core of its operation lies the radial velocity method, also known as the Doppler method, which allows for the determination of how much a star oscillates under the gravitational influence of an orbiting planet. However, even for giant planets, these oscillations are extremely tiny to be easily observed from Earth, on the order of hundreds of meters per second. And this is on the scale of a colossal object like a star. Even a typical red dwarf can be hundreds of thousands of kilometers in diameter, yet here the oscillations barely reach 100 meters. However, no matter how imperceptible these variations may seem, for rocky planets like Earth, these movements will be even smaller, by tens of times. For example, our own Earth causes the Sun to wobble imperceptibly at a mere 9 centimeters per second. Imagine that incredible precision! And what's most striking is that ESPRESSO aims for precisely this level of accuracy. It splits a star's light into its spectral components, and allows for the search of periodic shifts in the absorption or emission lines within that spectrum. In other words, as the star oscillates, moving towards and then away from Earth, its spectrum will appear slightly bluer, due to the Doppler effect, and then redder. If such shifts are regular and repeat at strictly fixed intervals, one can speak with a high degree of confidence about the probability of a planet existing in the system and even accurately determine its mass. It is noteworthy that the Doppler method, despite its effectiveness, has several specific limitations that are not always widely discussed. The most significant of these is the inability to obtain the exact mass of exoplanets. Instead, it only allows for the establishment of their minimum mass threshold. The root of this characteristic lies in the fact that astronomical instruments can only detect those oscillations of the parent star that are directed either directly towards or away from Earth. In an ideal scenario, where a planetary system is oriented, edge on, to us, meaning its orbital plane aligns with our line of sight, all gravitationally induced stellar oscillations would be fully registered as radial shifts, reaching their maximum expression. However, in practice, most planetary systems are oriented at a certain angle to the Earth observer, and this angle often remains unknown. Thus, the spectrograph records not the full amplitude of the stellar wobble, but only its projection, the component that causes the star's movement towards or away from our planet. Naturally, recording only a fraction of this oscillatory motion inevitably leads to determining only a fraction of the actual mass of the celestial body that initiated these oscillations. This circumstance presents a serious difficulty, as some detected signals, initially interpreted as signs of exoplanets, might actually originate from objects of a different nature, such as low-mass stars. Nevertheless, despite these nuances, Doppler spectroscopy remains one of the most effective approaches in detecting and verifying exoplanets today. Returning to the ESPRESSO instrument, it is strategically located at the European Southern Observatory's Very Large Telescope, VLT. This complex represents a unique engineering achievement, for 8-meter optical telescopes capable of functioning as a single giant instrument through interferometry. Notably, ESPRESSO possesses the flexibility to operate both individually with each of these telescopes and synchronously with all four, maximizing the interferometer's potential. All light information entering the instrument is pre-processed by an adaptive optics system, which effectively neutralizes the undesirable distortion and blurring effect caused by Earth's atmospheric turbulence. Thus, the outstanding resolving power, unprecedented precision, and exceptional sensitivity of the telescope itself, combined with the advanced design features of the ESPRESSO instrument, ensure phenomenal spectral accuracy. Before ESPRESSO, the astronomical community virtually lacked an instrument capable of such delicate measurements, with a precision of less than 10 centimeters per second. However, to address the ambitious task of researching Earth-like planets located in their stars' habitable zones, the creation of such a high-precision instrument became an urgent necessity. This is why González Hernández, one of the scientists involved in the initial discovery of Barnard B, joined the ESPRESSO development, and Creation Consortium alongside his colleagues from Switzerland, Italy, and Portugal. This collaboration provided his research group with guaranteed access to observation time on this cutting-edge device. As a result, they not only succeeded in confirming the existence of a planet around another of our closest stellar neighbors, Proxima Centauri, but also made an even more significant discovery, identifying a second planet in the same system, now known as Proxima Centauri d. And now, thanks to their tireless efforts, they have made another significant breakthrough, presenting the world with a new exoplanetary neighbor. Even when using a spectrograph of such exceptional stability as espresso, instantaneous and unambiguous detection of a planetary signal remains a challenging task. Evidence of gravitationally induced stellar oscillations is not accumulated instantaneously but gradually, as among the multitude of recorded data, the most pronounced signal had an orbital period of just over 3 Earth days. The object, which has been identified with high confidence as a full-fledged planet, has a mass approximately 0.37 times that of Earth. For context, this is roughly half the mass of Venus or, conversely, 3 times the mass of Mars. Given its extremely short orbital path and direct proximity to its parent star, this world is most likely devoid of a significant atmosphere. Its modest mass would probably be insufficient to retain a dense atmosphere, which would also be subject to the incessant destructive effects of powerful flares from the parent dwarf star. Such flare-ups are particularly characteristic of young red dwarfs. And although Barnard's star is considered a relatively old star, it cannot be described as quiet. Consequently, in the absence of an atmospheric cover, this planet has no chance of retaining liquid water on its surface, and its predicted temperature makes it entirely unsuitable for life as we know it. However, remarkably, the results of the study not only confirm the presence of a clear planetary signal, but also suggest that the existing data may conceal 3 more potential planet candidates. Notably, 2 of these hypothesized objects might be somewhat cooler. Signals corresponding to orbital periods of just over 2, 4, and nearly 6 days are not yet clear enough, and additional observations and in-depth research will be required for their definitive identification. Nevertheless, we can already preliminarily outline what these worlds might be if their existence is confirmed. For a star like Barnard's star, the so-called habitable zone, where liquid water could theoretically exist on the surface, extends within orbital periods of 10 to 40 Earth days. This means that if these candidates are indeed confirmed, they might be closer to this zone of life, but would still be exposed to more than twice the radiation of our own planet. The already confirmed planet, designated Barnard B, should be the most massive of all detected or hypothesized objects in this system, possessing 40% of Earth's mass. Meanwhile, the masses of the other candidates vary from 1/5 to 1/3 of our planet's mass. For comparison, the mass of Mars is only 1/10 that of Earth. Thus, all these exoplanetary worlds can be figuratively referred to as supermarses, emphasizing their size, which exceeds Mars but is significantly less than Earth. In other words, they can certainly be classified into a unique cohort of oddities, with no direct analogues in the solar system. However, it should not be forgotten that the current level of accuracy with which astronomers estimate their masses does not allow for full certainty regarding whether these objects belong to the category of supermarses, mini-Venuses, or sub-Mercuries. We do not yet have data on the angle at which this planetary system is inclined relative to our line of sight, so we only have an assumption about the minimum mass. In any case, astronomers can assert with sufficient confidence that they have indeed confirmed a rocky, i.e., Earth-like, planet in the immediate vicinity of the solar system. And of course, it is of immense interest that researchers are discovering precisely such worlds in nearby star systems. Incidentally, if such objects are so common in our nearest cosmic neighborhood, one can only imagine how vast their total number is throughout our entire galaxy. And what about the scale of the entire universe? Overall, this is a very positive sign, indicating that more Earth-mass planets are being discovered recently. This eloquently testifies to a significant breakthrough and steady development in the field of exoplanet research. And of course, it is always gratifying when the immediate vicinity of the Sun becomes more transparent to our understanding, so to speak. It is always fascinating to learn what neighbors surround us and what unique properties they possess.